This work is about the use of synthetic data for detection of fungal infections in histopathology reports. This work is in the context of Einstein, which is a project focused on automatic surveillance for fungal infections and other types of infections. There we see the automatic surveillance system at the center of the image, and this will allow clinicians and physicians to manually review diagnosis, to prevent infections, and to do retrospective surveillance. But the focus of our work is at the bottom left, which is algorithm-based detection of these fungal infections from different sources of data. The data can be from microbiology, histopathology, from antifungal prescriptions, or from radiology. A bit more background: infection-related mortality is a leading cause of early deaths for patients with hematological malignancy, and automatic surveillance can alleviate this problem or can help in this issue. For that, we use machine learning techniques that can identify infections, and machine learning methods rely on manually annotated data to work more accurately or for fine-tuning. But this can be a bottleneck because manually annotated data can be costly to produce, and it's not always easy to port to different domains when we have different infections. So the focus of this work, of this presentation, is to look at generative models as a source of training data for machine learning models. So this is specifically the method that we use. The generative model that we looked at is Google's Gemini, the version 1.5 Pro, and we applied it to this domain that I just described. The manually annotated dataset that we use for evaluation is the CFIR dataset that is publicly available. There's the reference there. And as classifier, we use gradient boosting, which has been shown to perform well on this data. There's another reference for this. And we compare the manual annotation with the synthetic datasets that we generated from Gemini, and we try two approaches. One is a balanced approach with the same amount of positive and negative reports generated, and another is following the distribution from the CFIR dataset to have a more realistic training dataset. So as an example of the kind of the data that is generated from generative models, we can see some positive and negative examples there. I won't go in detail, but you can see that the positive examples refer to fungal elements being present, and negative examples say that there is no evidence or there are no fungal elements. We ran an experiment with the generated data and the manual data to compare, and the task was to do binary classification of histopathology reports that have been manually annotated by clinicians using gradient boosting. And we see the results there, and we see at the top of the table the results for manual data are very high, as has been shown in previous work. And when we use the synthetic data, the results drop significantly, both in precision and recall, and even when we consider the distribution of CFIR. So the results are much lower for synthetic. And this is the main conclusion of this experiment, that when we use synthetic data, we without any out of the box, we can expect a big drop in precision and recall. We observe that a big limitation of our system is that the prompts that we use to generate do not have access to real data, and we think that this could improve the synthetic data that is generated. But for this, we would need a local installation and not use public APIs to access large language models because of privacy issues. So we couldn't be using real data via public APIs. So for future work, one of our goals is that to try better generation of prompts using real data, and also a combination of real and synthetic examples, and finally to rely on retrieval augmented generation for a more complex system. And that's the presentation.
Hello, my name is Arun Bajracharya, and I'm a knowledge graph engineer at Datum. Today, I'll be talking about how pharmacogenomic recommendations can be enhanced by integrating multi-source biomedical knowledge graphs. Pharmacogenomics is at the forefront of personalized medicine. It focuses on understanding how a person's genetic makeup influences their responses to medications. The goal is to ensure that patients receive the right drug at the right dose, minimizing adverse reactions and optimizing therapeutic outcomes. This is very important as genetic differences can cause patients to metabolize drugs differently, potentially leading to harmful side effects. PGX helps predict how a patient will respond to a medication, minimizing the risk of adverse reactions. Pharmacogenomics is also a key component in the broader field of precision medicine, helping to move healthcare toward more personalized, data-driven decision-making that benefits both patients and healthcare providers. The current challenge in pharmacogenomics implementation is that the data originates from multiple sources, each using different formats and terminologies. For instance, data from CBK guidelines, FDA labels, and Pharmacogenomic might have different unique structures, vocabularies, and data models. This diversity makes it difficult to harmonize the data into a single, cohesive format that can be easily analyzed. The lack of interoperability means that data from multiple sources cannot be seamlessly combined. Healthcare providers may face difficulty in accessing all relevant PGX information within their workflow, leading to missed opportunities for personalized drug recommendations. So, Knowledge Graph is an ideal solution to integrate and structure diverse pharmacogenomics data. By using a knowledge graph, we can unify data from various sources, creating a single cohesive ontology that makes the data accessible, interoperable, and actionable. Our knowledge graph maps PGX data sources into the UMLS, Unified Medical Language System, using SCOS, Simple Knowledge Organization System, as the primary ontology. This standardized approach enables us to map complex relationships, unify terminologies, and ensure consistency. Here's an example of how we have resolved two different guidelines into a standard ontology. We have pharmacogenomics recommendations from FDA and CBK guidelines, which are connected to the drug, gene, and phenotype that are resolved to UMLS through the SCOS ontology. By resolving these into a standard ontology, we harmonize the language, making it easier to integrate and compare data across various sources. In addition, we have enhanced knowledge graph by integrating large language models, enabling users to query the graph for precise, reliable, and contextually accurate information. This integration acts as a safeguard against hallucinations often associated with LLMs, ensuring that all recommendations are grounded in the validated biomedical knowledge within the graph. So in a nutshell, our application takes in pharmacogenomics guidelines from various validated sources and are combined into a cohesive, interoperable knowledge graph through which the recommendations are provided to the end users in the application. So here's a quick demo of our pharmacogenomic clinical decision support system, which is designed specifically for clinicians and healthcare professionals. Users can select the drug they intend to prescribe and input the patient's genetic and phenotype information. The app then leverages our knowledge graph to generate a recommendation drawing from validated and trusted guidelines. Additionally, users can take it a step further by querying the application, which utilizes a large language model to provide deeper insights and explanations, ensuring that recommendations are both comprehensive and grounded in reliable data. Users can also get a full detailed report of the chosen drug, which includes phenoconversion information and also all impacted medications for the gene phenotype pair of the patient. So in conclusion, our application enhances personalization through knowledge graphs, which enables tailored drug recommendations by unifying diverse pharmacogenomic data sources. It also improves accuracy and reliability. The integration of knowledge graph with LLMs acts as a safeguard against hallucination, ensuring precise and evidence-backed recommendations. Healthcare providers can also ask follow-up questions, improving understanding and confidence in the recommendations through contextually accurate responses. The system empowers healthcare providers to make well-informed, personalized decisions based on a patient's genetic profile. This approach supports the evolving landscape of personalized medicine, driving more accurate, transparent, and explainable AI-driven healthcare applications. Thank you for your time.
Hello, everyone. My name is Matt South. I'm a software engineer from Openclinical and Birmingham University. And I'd like to present some work that I've been doing with the WHO Smart Guideline Digital Adaptation Kit, DAC, for antenatal care. So the DAC and the Smart Guidelines project first came to my attention last year during some discussions that MCBK UK were leading with NICE. My super brief summary of them is that they provide a template for healthcare professionals to start communicating to software professionals what they'd like from a digital pathway implementation for a particular condition. In the L1, L5 model that we talk about, and I've lifted this image from the DAC. It sits very much at the L2 level, and it consists of references to guidelines, personas, user scenarios, relevant data elements, workflows, decision tables, indicators, and performance metrics and functional requirements. It's a really nice encapsulation of requirements for the later stages, the later layers. At Openclinical, we been exploring the viability of creating a repository of computer interpretable guidelines at L3 using a language called Proforma that John Fox and colleagues developed for this purpose almost 20 years ago. Openclinical is a repository, openclinical.net is a repository of the models created by John and his colleagues in a closed source system called Talis. But in recent years, we've been trying to be more open and migrate the existing models to an open source framework. We call this framework Ops, and you can find it on gitlab.com/openclinical and find the work that I'm presenting here. So one of the projects we've been doing this year is an attempt to implement as much as we can from the ANC Smart Guideline in Ops, and the results are on, as I said, just on GitLab. And if we do this, we see, and if you run it and install it yourself, then you'll see this web page. And the process that we've used is to take the data element spreadsheet and script the conversion of that into Proforma data definitions. And then we've manually converted the DMN tables into Proforma workflow snippets. And if we look at one of them, the preeclampsia number 17, then it boils down to about 10 different tasks. The first task is to collect the blood pressure of our patient, and this is quite high for this patient, so we wait for 10 to 15 minutes and then collect it again. And when we collect it again, this patient's blood pressure is still high, slightly lower, but still high. So then we ask some more questions, gather some more symptoms, and ask for a urine dipstick result. For this patient, it's not concerning, so then the guideline suggests doing some hypertension counselling. Their blood pressure is still high. And so you can see how we then taken the spreadsheets and we've created some working software, and we're in the process of doing that for many of the other, all of the other decisions in the Smart Guideline DAC. So the 4 informal conclusions are from this, that this working software provides a useful sense checking on the scope of the DAC, hopefully at an unexpected lower cost than delivering the full solution, and hopefully prompts some conversations about usability. And those are the pros. The cons are it's a proprietary, though open source format, and a manual development process, quite slow. But a useful consolidation process for going for checking these DACs, these L2 DACs. And the future work, we want to finish this exercise, and help is if you're interested and you want to help, that would be great. We want to adapt our editor to start producing fire plan definitions and get off our proprietary format as much as we can. We'd like to integrate Open Concept Lab as the source of data definitions, and certainly explore that. And the reason we're doing this is to create our own custom DACs for multiple long-term conditions in a project called DigiPaths. Thank you very much.
Hello, everyone. My name is Kelsey Rook. I'm a graduate student at Rensselaer Polytechnic Institute, and today I'll be telling you about semantic modeling of evidence for psychometric instrument usage. Most psychometric assessments are available in an unstructured text format, and clinicians typically find them through word of mouth, literature searches, or other internet searches. This format, unfortunately, results in minimal empirical justification for the usage of a tool, which further isn't supportive of evidence-based assessment. To address this lack of standardized knowledge infrastructure, we have developed the Psychometric Ontology of Experiences and Measures, or POEM. And to illustrate how POEM models instruments, I'll be telling you about the ARCADS 47, which you can see a copy of on the left. The ARCADS 47 is the original instrument in the Revised Children's Anxiety and Depression Scale, which is an instrument family for assessing anxiety and depression in children from ages 8 to 18. POEM models instrument entities such as instrument families, scales, items, and response options, as well as the underlying concepts that scales and items aim to measure in individuals. So for example, on the left there, you can see that all items in the major depressive disorder scale are highlighted in red, and the scale, of course, tries to measure major depressive disorder. One of the questions in the scale, question 6, is nothing is much fun anymore, and this question assesses the symptom anhedonia. But how can we be confident that a question or scale actually measures the concept that it claims to? Of course, we have plentiful research studies that measure the quality of assessment instruments, but there are still some challenges that prevent good evidence reporting. Particular challenges include a general lack of standardized knowledge infrastructure to organize and aggregate assessment tools and properly evaluate them for strength of evidence for use. Second, there's a lack of support for tracing the derivation of instruments, and without the structured representation, it's difficult to associate evidence with the appropriate instrument in a family. There's also varied quality criteria metrics across research studies, which adds difficulty in comparing assessment instruments. And finally, there's a lack of representation of complex context metadata, which makes it difficult to determine whether your purpose for using an assessment matches the original intended context, or if it's even been validated for the group that you want to use it with. To tackle these challenges, we're working on an extension to POEM for psychometric evidence modeling. Centrally, we have the evidence class, which is from the evidence and conclusion ontology, which is a type of information used to support an assertion. In this case, the assertion that some item or scale measures what it claims to for a particular cohort and context. Next, we have the study cohort ontology, which supports descriptions of study cohorts, including demographic information. And we have the statistics ontology, STATO, which contains a lot of statistical tests and measures that are often used as psychometric evidence. Importantly, POEM also supports provenance tracking of authorship, translation, and modification of assessments, which further supports correct evidence attribution. The evidence gathering workflow with POEM includes gathering studies, aggregating and annotating the evidence from them, and adding this evidence to a database. And from there, semantic technology experts can then align this evidence with the POEM ontology and store the linked data for retrieval. Our ongoing work includes supporting more complex study evidence, for example, those with multiple cohorts or those that compare the same cohort over a time interval, as well as more advanced provenance modeling, such as for language translation and cultural translations. In conclusion, the current knowledge base of psychometric assessments and evidence is pretty fragmented and opaque due to the lack of semantic infrastructure supporting it, but we believe that ontologies are a good solution for this. Thank you.